Okay, let's start this review for the midterm. I'll start with the first set of charts, which corresponds to chapter 1. And the main points here was the notion of services and applications, which was laying the groundwork for how communication networks, by offering just a few basic services, can support many applications. We'll come later on and talk to the notion of layers in the next chapter, but let me summarize the main points here in chapter 1. The first one had to do with message switching as appeared in the context of telegraphs. And here basically when you had messages that traversed the network, and basically the messages required addresses to denote where they were coming from and where they were going. And the basic function in the network was to be able to route the telegraphs from one node to the next so that the message progressively got from the input and worked its way to the desired destination. And this process is called store and forward. And it appears later in the context of packet switching networks. Okay, so the elements of the telegraph network was a service which involved the switching of messages from inputs to outputs. This required addressing source and destination addresses. The procedure involved a store and forwarding across the network. And the routing had to be built into the network so that by looking at the destination addresses, it was possible to determine what the next hop should be. So that's one of the earliest forms of network architecture. The next one had to do with telephone networks. We use circuit switching. So the basic service there is establishing a circuit from an input to an output. And the telephone network did this through a signaling system that would set up the call from the input to the output. The inputs and outputs were specified by a numbering system that assigned basically what we call a telephone number, and which was used to designate the input and the output. And the job of the network was to set up a connection from the input to the output all the way across the network. Those were the basic elements of what we discussed in the first lecture. But then we started looking at how the introduction of computers, in a sense, revived the kind of techniques that had been introduced in the telegraph system, except now we were interested in initially communicating from terminals to computers, and the terminals had to send messages, directions, instructions to the computer, and these were in the form of payloads inside of frames. And there were also headers, which contained control information, and check bits, CRC bits. So messages went from terminals to a computer, and then the responses came back in the other direction. So you see, this is a direct extension of the type of techniques that were introduced with telegraphs. Things got more interesting as computers proliferated, and there was a need to connect not just terminals to computers, but computers to computers. So we needed computer-to-computer networks, and that gave rise to packet switching. What happened was that in message switching, there was no limit on the size of the messages, and hence if you had very long messages, and very short messages, the long messages could impose long delays on the short messages, impacting their interactivity. And so what packet switching introduced was a limit on the size of the blocks that a network would handle. And this block was called a packet. And so packets had a maximum size. And if messages were too long, they would be broken into multiple packets. So that was the origin of packet switching. The first packet switching networks involved packet switches that were all identical, interconnected with identical communication lines. And just as in the case of message switching, packets were transferred across the network in store and forward fashion. And the destination address and routing tables in the switches told when a message arrived, the destination was consulted, used to access the table, and that would tell it what the next hop would be. That was the origin of packet switching. Things got a little bit more interesting with internet, where there was an interest in connecting computers. This one, for example, they were connected to different networks. This network is different than that network. And so the internet was created, which introduced a router as a means to interconnect networks of different type. And that IP stands for Internet Protocol, and it's a protocol that's used to communicate across the internet. Okay, and so you see that the same type of concepts that from telephony in terms of addressing and routing made its way into the first computer networks. So let's look at the material from chapter 2, which started going into internet protocols in more detail. Chapter 2 is probably the most important chapter in the book because it talks about how networks are organized, in other words, their architectures, and it introduces the fundamental concepts involved here. Okay, networks involve many different functions in order to be able to effect the transfer of messages across a large network, and so they're organized into layers. Oops. Let's see. What am I doing here? Okay, there we go. Okay, they're organized into layers, and we saw that a little bit later we introduced the OSI reference layer, but basically in the beginning we were introducing that HTTP, an application layer protocol, operated on top of a transport layer protocol, TCP, which in turn operated on top of Internet Protocol. Okay. So let's go back to the way I had it before. Okay. So each layer has its own protocol. Okay, for example, here's HTTP. Okay, and the protocol is designed so that the two sides behave as if they're directly connected. So the protocol defines messages that are exchanged between the entities, the participants in the protocol, and the protocols get their job done by exchanging messages. These messages have control information, a variety of things like that. And HTTP is the application layer protocol that supports browsing. Okay, now this appearance of protocols being directly connected, in fact, is not true. They act as if they're connected, but in fact, they use the service of the layer below. And so HTTP uses TCP as the layer below. And so in order for these two to appear to be directly connected, what TCP does is it provides an abstraction of two pipes, one from client to server, one from server to client, and TCP then does the work of enabling the smooth transfer of bytes from one direction to the other and then back. So TCP establishes this connection between these two servers. Okay, and we saw that it involved port numbers. Okay, and later on we also saw that it involved IP addresses, which are below this layer. There's other application layer protocols required to enable this type of connectivity, and one of them is DNS protocol. DNS provides a mapping. It's a distributed database that provides a mapping between names of machines and IP addresses, and that enables machines to find out the IP addresses of other machines and hence to communicate. And so let's make this a little bit smaller, a little bigger. Okay, that's good. And so the combination of these application layer protocols, DNS, HTTP, transport layer under it, TCP, enable applications to operate across the internet. We very briefly, at this point, introduced UDP, which is the other type of transport layer protocol that, unlike TCP, is intended to send individual datagrams, individual messages, without setting up connections. Okay, so then we went a little bit into more detail in terms of the layering, the theory of layering, and the OSI reference model, which was developed to do that. And we introduced a 7-layer OSI reference model, which includes the transport layer and application layer we had discussed before, but that has others. At the very bottom, there's a physical layer, which deals with the transfer of bits between directly connected machines. Next was the data link layer, which involves the exchange of frames or blocks of information between directly connected machines. Next was the network layer, which involves the transfer of blocks of information called packets across machines that are not directly connected. You have to go over multiple hops. Okay, so that's a network layer. And a particular case of the network layer is the internet layer, where packets traverse a network of networks, an internet, okay, and to connect two different computers. On top of the network layer is a transport layer. The transport layer only appears is an end-to-end protocol, in that the protocols reside only in the end system machines, not inside the network. Okay, and the examples that we had was TCP and UDP. These reside only at the client and server, not inside the network. There were other layers. There was session layer, presentation layer, okay, which are not used, and then the application layer. So in essence, then, what we have is a 5-layer stack that is used in practice: physical, data link, network, transport, and application. The next section should how all of these layers come together in the context of internet. We explain how internet works, okay, and how the two services, reliable stream service of TCP and datagram service of UDP, enable many, many different types of applications. Okay, we explain how IP works, how packets are transferred from a machine connected to a network, and how the addressing designates the destination network. Once you get to the destination network, you have to figure out the host ID. What computer do you deliver that message to? Okay, so that's the way internet works. And the interesting thing is that internet protocol is used throughout to communicate over many different kinds of networks, but above it, everything is the same: TCP, UDP, and the various types of protocols. Okay? In this chapter 2, we also in the lectures for chapter 2, we explain how internet addressing works, host ID and net ID. We discussed the 32-bit addressing. And in Lab 1, you got practice to work with, to identify source IP addresses, destination IP addresses, and so forth. What we saw is that at the end network here, okay, you've determined that remember the IP address, net ID, so you've got here, and so you've got a host ID. You have to figure out what host you should send it, and that last hop is done using the protocol of this network. And to do that connection, that transfer, you need the physical address, a MAC address, that corresponds to the last hop to deliver that packet to the end machine. And so for that, you need the MAC address or physical address, which is 48 bits. If the network is an Ethernet network, you use Ethernet addressing. If it's Wi-Fi, you use Wi-Fi addressing, and so forth. Okay, and so the way the different layers work together is by encapsulation. For example, you take the IP packet with its header and you insert it in the data link layer protocol, in this case Ethernet, and you put the headers for Ethernet and the check bits, and then you operate over Ethernet. Okay, I won't repeat this example here, but I encourage you to go through it in detail, because this explains how packets are transferred across one network, this Ethernet network, for example, but as well the operation of the router in interconnecting one network with a different network. Okay, this is just a review, so I can't go in, don't have time to go into detail on that, but I really encourage you to do that. And also to look at these examples, which show how Wireshark operates and which corresponds to what you did in Lab 1. Okay. And then what we did is we looked at two types of application layer protocols here. One was HTTP, which is used for browsing the web. Okay. And the other one was a little bit more unusual, which is real-time protocol, which provides you with the ability to put sequence numbers and timestamps on blocks of information that you transmit over the internet. And in particular, this is used to transmit real-time media. Voice for voice over IP communications, video for real-time conferencing, and so forth. So RTP is used at the application layer to take your voice signal, for example, put it in packets, put timestamps and sequence numbers that can then be transmitted across the internet to carry out real-time voice communications. We introduced a session initiation protocol, which provides some of the signaling functions that the old telephony networks provided to set up the connection, establish the association between this machine and this machine so that they can exchange voice packets. Okay, the next topic was sockets, and sockets basically teach you how, as a programmer, you can access the services provided by TCP and UDP. And basically, these are done through an API, okay, called a socket. At the below the API in the kernel of the operating system, you have port numbers and IP that provide you with TCP or UDP transfer. Above it, you have descriptors that allow you to refer to the types of transfers that you require in your application. And in these charts, we explain how the different types of transfers work. Okay, so that completes chapter 2. And as I said, chapter 2 is probably the most important chapter in the entire course. If you understand this, you basically understand how internet works. Okay, let's now move to the next one. We then started looking at some physical layer aspects. We talked about how digital communications takes place. We covered it very, very briefly, but we talked about binary signals. So you have some zeros and ones across media, such as cables or radio. We talked about limits in terms of how fast you can communicate across a channel that has bandwidth W hertz, and it's 2W pulses per second. But the number of bits that you can transmit has to do with how many levels of these pulses you use. So if you use M levels, 2 to the M levels, you transmit M bits per pulse, and so you get 2WM bits per second. But your ability to increase the speed that way is limited by noise. Okay, noise makes it difficult to operate with too many levels because you start making errors in detecting between one level and the other. And so we introduced the Shannon channel capacity, which provides the theoretical maximum number of bits per second that you can transmit over a channel that's got bandwidth WC, and it has signal to noise ratio SNR here. It's given by this expression. And then we gave a number of examples for different types of media, for copper wires, for coaxial, for radio, for optical fiber, and saw the types of bit rates that are achievable with this kind of systems. In addition, we also gave a sense as to how these media are used, how copper wires are used in the telephone network, how copper wires are used in Ethernet LANs, how coaxial cable is used, and how cable modem networks, Rogers types of networks, operate. And then we also gave a brief introduction and saw the amazing bandwidths that are possible with optical fiber. Okay, and very briefly, with just a few charts, we explain how cellular networks work. Then we got into sort of going back into these notions of headers and checksums. We explained how error detection works and the role of those checksums in being able to detect errors that occur in communications. And what we explained is that all of the error detection capabilities depend on the fact that the code words that are sent into a channel satisfy a pattern, and hence all the receiver does is says, is it a valid pattern or not? And if it's a valid pattern, it accepts it. And so what the transmitter does is it takes K bits, K information bits, and each block of K bits, it maps into a corresponding code word, which is then transmitted across. If you're lucky, that code word arrives without error, and the receiver then decodes it back into the original K bits. And so to work, what you need to do is to have it difficult for the channel to convert one code word into a different code word, because that's when errors occur. When a code word appears here, it'll be detected as correct, and if it happens that the original code word is different, then you're going to make errors. Okay. So we gave 3 examples. We talked about parity bits, single parity check code. We talked about internet checksum. Okay, and we talked about polynomial codes. And we explained how each one of these can provide error detection. And we noted that in internet headers, internet checksum is used, but almost everywhere else, generated polynomials are used, which are more powerful. We also did a number of calculations. Let's see, where are they here? In terms of what's the problem if the channel introduces errors independently from bit to bit, then you can do these kind of calculations, which take you into geometric probability calculations and binomial probability calculations to find the probability of error. Okay, so that was error detection. Most recently, let's see. Most recently, we've been looking at ARQ, and let's start over here. And basically, ARQ assumes that you've got checksums that are effective. In other words, you're using one of those error control techniques that's effective. And basically, what you do is you take the bits from, let's say, if this is in the physical, if this is the data link layer, you take bits, you put check bits, and you sequence numbers and send it to the other side. If they're correct, the bits are accepted, transferred to the upper layer, but as well, acknowledgements are sent in the reverse direction. And the first type of ARQ protocol we considered was stop and wait, where you send, let's go over here, no, let's see, here, where you send the block of information and then you just wait until an acknowledgement comes in. If an acknowledgement comes in and says the block was received correctly, then you go and accept another block and start working on that to get it to the other side. If you don't get an acknowledgement within a certain period of time, you set a timer. So the timer goes off and says, oops, we didn't get the ACK for that one, and you send the block again. Okay, and so this is a very simple type of protocol, and what we did was we did an analysis of how efficient that was. And during this period, this section here, you're transmitting bits, but if the time that you have to wait is a long time before you hear back, here's the ACK coming back. If this is long relative to this, then we found stop and wait is quite inefficient. We derived a formula for that. We worked out some numbers, and we saw that this is very inefficient when the delay bandwidth product, this term over here, that's the killer. Okay, if this number is big relative to 1, your efficiency is going to be poor. Oops, let's see. I want to go back. So how do you fix that? Well, you fix that. Oh, yeah, sorry. Before we go there, if there are errors, then that's what's going to force you to do retransmissions. And so we also derived an expression of how many times on average, if PF is a probability that the frame is in error, how many times are we going to have to resend it? And it's 1 over 1 minus PF. Okay, and when we put it back into the efficiency calculation, you get this expression. And now you have not only the delay bandwidth product hurting you, you have the frame loss probability hurting you. And so you do this calculation again for different types of bit error rates, and you see, of course, that it does poorly. Now, this here is 1 minus PF is equal to this, is equal to e to the minus NFPF. That's a very useful expression when you're doing calculations, because the probability of frame error actually is determined by the probability of bit error. So you need to know this expression. Okay, so how can you improve over stop and wait? Don't stop. No, sorry, no stop. Don't wait. Keep transmitting. So you send many, okay, and you just keep sending. Now, of course, your sequence numbers have to be bigger. You need more counters, more timers to tell you when to return, when you should have heard an ACK and to retransmit. But the receiver stays the same. It's only looking for a particular frame, which is denoted by R next. Okay, and as last, okay, was the last frame that was acknowledged. No, the oldest frame that is yet to be acknowledged. Okay, so that's, this guy's waiting to hear for that, and this guy's waiting to receive that. Okay, and so what you have is a send window over here, and you have a set of numbers that you're allowed to use, and this moves kind of like a wedge of a pie that slides forward as you get acknowledgments. When you get an acknowledgement, this guy says, oh, okay, got this, this moves forward, this guy moves this way, and WS ahead of that also moves. That's your wedge. Okay. We looked at a particular type of retransmission called selective repeat. Selective repeat's a little bit makes another change. Instead of just accepting 1, now you have a bigger window to accept more frames. And now, so you have a window at the transmitter, a window at the receiver. And so here's what they look like. Okay, and you should know how these operate as when you get acknowledgments here or when you get arrivals in here. You should see how these move forward as acknowledgments or frames arrive. Okay, you should be able to rework this diagram, which shows selective repeat in detail. You should be able to do these kinds of determinations where you have packets arriving at a certain time, certain sequence numbers, and these basically correspond to the state of your send window and your receive window. Okay. We derived the expression for the efficiency for stop and wait. Very nice, simple formula. And indeed, when we do the calculation, we see that it can improve vastly over selective repeat. It's much, much better than stop and wait. Okay. And then the last topic we considered was TCP. TCP, we already spoke about it just a few minutes ago when we started this lecture. Okay, it provides reliable stream service. And now that we had covered ARQ, now we were in a position to explain how TCP error control works, except that TCP put in a couple of new wrinkles. One of them is that TCP doesn't work with frames. It works with byte streams. And so the sequence numbering in TCP counts the first byte and the last byte that is being sent in a TCP segment. This is a segment. So the operation is very similar, but the sequence numbers are 32-bit numbers that count the bytes that are being carried in a segment. Okay. The sequence numbers, when the TCP connection is set up, the initial sequence number has to be established. It's not 0. It doesn't start at 0 every time. It starts at a given initial sequence number that's calculated by each of the transmitter at the sender and the transmitter at the receiver in TCP. And so here we have the three-way handshake, but we also show how the sequence number is selected. Okay, and the other thing that we show in here is that TCP not only uses a three-way handshake to start the connection, but it uses a graceful close, a pair of other handshakes, to close the connection in each direction. Remember, TCP has two connections, one in each direction, and each one is closed separately. Then we gave some examples that show the operation of the three-way handshake, the initial sequence numbers, and the graceful close for TCP. Okay. Now, the other thing that TCP is doing is, as you're sending information back and forth, it's sending acknowledgments, sending sequence numbers. Here's a segment. It starts with this sequence number, and it goes up to this sequence number. And then the acknowledgement has to come back in the reverse direction and say, I've got all of your bytes up to this point. And so if you should be able to look into Wireshark frame and be able to say, oh, here's the sequence numbers. Okay. The TCP does not use selective repeat by default. Okay, it uses something closer to that rnext, send many, receive rnext in the version over here. Okay, but TCP does have an option to use selective ARQ, and that was explained here. And then the final topics was flow control. Flow control was to prevent one machine from overwhelming the other. Overwhelming in the sense of sending so many bytes that it overflows the buffers in the receiving machine. And so TCP flow control has a advertised window, WA, that has a receiver tell the transmitter, I got this much room, don't send more bytes than that, and has the sender ensuring that it complies. Okay. We had some discussion in terms of how timeouts are calculated. And then the final topic was how TCP does congestion control. Congestion control is different than flow control. Congestion control is when packets are lost inside the internet. Okay, so you might have many flows in here. Let's say many of these are TCP flows. And what happens is if this gets congested, packets will get lost. Then the TCP connections at the end will have to go retransmit those frames. Okay, and if not handled properly, that'll cause more congestion in here. And so what TCP congestion control does, it has the senders monitoring the rate at which frames or acknowledgments are coming back to determine if everything is okay or not. If it's okay, they continue sending at their speed, but if it's not okay, they slow down. Okay, and the process of how you do that is through the mechanism of a congestion window, CWN. Where is it? Congestion window here, CWND. Okay, and so what we did, we explained how TCP starts by transmitting one frame. If it comes back fast, then it doubles the congestion window that says, oh, I can send 2. If they come back, then it doubles it again to 4. So it's going up exponentially here. Okay, and if that weren't checked, it would go up to and transmit as fast as it could, and it would only stop if it ran out of segments to send. But what can happen is that, of course, if all these machines had lots of frames, lots of segments to send, inevitably you would drive this guy into congestion. And so what TCP congestion control is it adaptively calculates a threshold. And when it hits a threshold, when the congestion window hits the threshold, instead of going up exponentially, it starts going linearly. Okay, and so we explained how that happens. And the linearly is to try to avoid losing packets, but nevertheless it's increasing. So if continued for sufficiently long, you're going to lose the packet. And you can detect when you've lost packets because you get duplicate acts. And so when that happens, you say, oops, I've gone too far. And what it does is it restarts, going slow, and then readjusts, recalculates. You see here was a congestion window. It recalculates it, multiplies it by half. Okay, and through this process, it goes fast, slow until it hits congestion, and then it does it all over again. There's a trick that tries to account for when this has happened, and instead of going down, it does the calculation of where you would have been, and so it doesn't go all the way down. It tries to stay here. Okay, and that was what the fast retransmit and fast recovery method was. Okay. The other thing that TCP has is random early detection, and basically what it does is, oops, here, let's go back again, here. Okay, when this starts getting congested and the buffer fills up, then many of the TCP flows through here are going to start losing packets, and they're all going to slow down at the same time. Okay, and so they'll slow down, but then they'll speed up at the same time, and again they'll cause congestion here. So what red does is it tries to prevent the synchronization of the transmitters by monitoring the occupancy of the buffer. And as the buffer becomes more full, it'll start discarding segments on purpose to slow some of the senders. Okay, and so what it does, going over here, when things are good, it doesn't drop any, but it starts getting congested. It starts dropping them with this probability, okay, until it fills up. And so the idea is to start selectively causing some of the TCP connections to slow down, but not all of them, okay? And as you get more congested, you start asking more of them to slow down, and so that attempts to remedy the onset of congestion. Okay, so let's see. So covered all the topics that we've covered in the course. I focused on the concepts. You have to go look at the homework problems and some of the other problems at the end of the chapter to exercise, to think about how these concepts apply. I discussed Lab 1. Lab 2 had a number of utilities, ping, traceroute, netstat, and so forth, and you should know what these functions do. Okay, so that completes the review, and in the next lecture on Friday, I'll take questions regarding the topics we covered, which will be covered in the midterm. It's helpful to me if you send me by email questions on things that aren't clear for you, so I can try to organize the the session, so that I can group similar questions together and answer them all at once. Okay, so I hope you find this lecture, this presentation useful. Thank you.